Alright, this question is asking, what is the electron configuration for manganese? Now looking at a periodic table, you'll see that the atomic number for manganese is 25. What that means is that there's 25 protons, but we know that if there's 25 protons, then the matching number of electrons that you need to be neutral is 25. So we can go ahead and start with that number here as we look to do two things. Consider an orbital diagram, kind of where the electrons are, and then consider electron configuration, kind of the textual representation of the, electron distribution within the atom manganese. So let's go ahead and start. We know that in the ordering of orbitals according to their energy, the lowest energy is the 1s. It's the spherical, and the principal energy is 1. The L value is 0. The shape is spherical. Then we have the 2s. And because of shielding, we know that the 2p is just a little bit above it. And now the principal quantum number is 2. And you can have always two types of orbitals if you have a principal quantum number of 2. It turns out the same thing for 3. If we have a principal quantum number of 3, then we can have the s. We can have the p. We can also have the d. Now I'm going to put that a little bit higher so that we can put somebody in the gap between the 3d and the 3p. And that is the 4s. We said for shielding reasons, this can be just a little bit lower. I gave it more room here so we can see the electrons and such, but 4s is really, really close to 3d. We can say it slips underneath. In some cases, it actually rises above, but we're going to put it there. So now we can go ahead and put those 25 electrons in. I'll use a different color, just all blue. We need to go up and down. Pauli exclusion principle says these orbitals have 2 electrons that can be held, but they have to have opposite spins. So only 2. We fill up the next level with 2 more electrons. And I'm drawing it the wrong way. You shouldn't do it paired up. I'll do it the right way on the 3p. It's just good habit. Yes, we pair it up here because it's the lowest energy orbital, but it's good habit if these are equal energy just to go ahead and fill them up half filled, or we say single, stay single until as long as you can, and then come back and fill up the 3 half orbitals. So now we have 10, 2, 4, 6, 8, 10, 12, 14, 16, 18. If I go ahead and finish off the 4s, then all I have is 5 electrons left in the orbital diagram. So I'll put those in 1, 2, 3, 4, 5. We have 5 half-filled 3D orbitals. Now I do want to mention, looking at the periodic table, that if we would have stopped at argon right here, we would have been finished with the 3rd row. And remember, as you look at a periodic table, it's really your guide to how you organize these horizontal lines labeled 1s, 2s, 2p, and such. Those horizontal lines are labeled as such just as you read a periodic any book, you read from left to right, top to bottom. 1s, 2s, 2p. We're in the 2nd row, and it's the p block. This is called the S block. Come back to the S block in the 3rd row. 1, 2, 3. 3s, 3p. You say, well, I don't know where to put the d's. Well, if you keep reading, you do. So there's the 3s, 3p. This is the 4s, and it just comes naturally. Now, the only thing you need to remember is that it's not the 4d, it's the 3d. It just drops one number. So if this is a 4, this is a 3. If this is a 5, this is a 4, and on down the line. So you can kind of use the periodic table to help you set up those black, horizontal lines I have, plus the letters, if you're not sure where to put them. So this would be argon. The reason I pointed that out also is when we go to E configuration, we can have the full, electron configuration where we have 1s2, 2s2, 2p6, and we keep on going, 3s2, 3p6, and then finish it off with a 4s2. Now there's some ways we can do the 3d5 and then the 4s. We can flip those, but this is acceptable. Or we can abbreviate all of this and just say, hey, that's argon. that's the state of argon, and so we put a bracket and say, then we'll just have the valence electrons noted, 4s2, 3d5. And again, you might see in a textbook, they write it as 3d5, 4s2. And the reason why they do that sometimes is because if you were to take 2 electrons, if we were to have this ionized, and the ionization energy is pretty low for metals and higher for those non-metals to the top right, we would always take from the 4s. You don't take from the 3d. It has to do with the fact that the energies of these start to switch and change. The 3d gets down lower than the 4s. So these 2 electrons we'd start stealing from the 4s and not the d. So that's sometimes why you'll see it in this convention. Hey, thank you. I'll accept either one of these 2. Bye-bye.